Our first panelist, Dr. Çetinkaya-Rundel, is professor of the practice and the director of the undergraduate studies at the Department of Statistical Science and an affiliated faculty in the Computational Media, Arts and Cultures program at Duke University. Her work focuses on innovation in statistics and data science pedagogy, with an emphasis on computing reproducible research, student-centered learning, and open source education. She works on integrating computation into the undergraduate statistics curriculum using reproducible research methodologies and analysis of real and complex data sets. Our second panelist, Dr. Tammy Kolda, is an independent mathematical consultant under the auspices of her company MathSci.ai, based in California and founded in 2021. From 1999 to 2021, she was a distinguished member of the technical staff at Sandia National Laboratories in Livermore, California. She is a member of the U.S. National Academy of Engineering, a fellow of the Society for Industrial and Applied Mathematics, and fellow of the Association for Computing Machinery. Her research is in the broad domain of mathematical data science. She has authored more than 75 journal articles, conference proceeding papers, and book chapters. She's additionally the author of 2 books, Tensor Decompositions for Data Science and Unlocking LaTeX Graphics, a concise guide to TIXI, PGF, and PGF plots. In terms of professional service, she's currently the SIAM Vice President for Publications and chair of the new SIAM Activity Group on Equity, Diversity, and Inclusion. Our third panelist, Dr. Rachel or Ray Levy, is an award-winning writer, researcher, and educator who has dedicated her career to making mathematical modeling, data science, and AI belong to everyone. She is the inaugural executive director of the NC State Data Science and AI Academy and professor of mathematics at NC State University. She incubates data science research partnerships within the NC State system across North Carolina and beyond, leads the design and implementation of the Data Science Academy's all-campus data science accessible project-based teaching and learning course model, and communicates about data science with national and international audiences. Okay, that is plenty from me. For the rest of the panel, you'll be hearing from these 3 brilliant folks. We'll be doing a combination of some of the pre-submitted panelist questions, some questions that we've written, and then submitted questions. So we have a great audience. Audience, please feel free to submit questions into the Q&A, and we'll be moderating those as we go. Okay, my first question for the 3 of you, could you please introduce yourself and briefly describe your pathway into data science and its mathematics? I think I would suggest we go in the order Monet, then Tammy, then Ray, if that's okay.
Sure, thanks. Yeah, and thanks for the introduction and the invite. So, as you mentioned, I'm a professor of statistics, though I've sort of feel like the latter half of my career, I focused more on teaching data science. And when I think about like how I ended up here, I studied actuarial science in undergrad, and I don't have a good reason for it. My parents wanted me to go to business school, and it was the mathiest thing you can do in business school, and that's why I studied it. And I did take some sort of modeling and stats courses as part of the required curriculum and worked as an actuary for a couple of years. And at some point decided maybe I will go to graduate school, and was thinking about sort of reflecting on my undergrad work and the work that I had been doing as an actuary, and realized the pieces that I really enjoy are the pieces where I actually touch data. Like there was a lot of data cleaning in the type of work I was doing as an actuary. They would send us these rosters of employees and we would calculate retirement benefits for them, but their birth dates would change from one year to another in the file. So you had to check for these consistencies and stuff. And I enjoyed those pieces. And I was like, I think I used to be okay at math, but I really like data. So that's how I decided statistics. And it was, to be perfectly honest, during my stats PhD that, I don't know, maybe 3 years into it, I realized why anyone ever asked me to take linear algebra. Like it took me a while to put the pieces together. And I think it took me a while because either I was thinking about it that way or it was presented that way as like these modular things that, you know, these veggies I should eat that I should just believe are good for me, but the connections weren't entirely clear to me. And it took a little bit more work to get there. So nowadays, when I'm teaching, I think about trying to make those connections a little earlier so people don't feel like they don't know why they're learning the things they're learning. But that's how I ended up in graduate school. And it was during graduate school that I fell in love with one, teaching, two, actually programming. I had never written code before then. And also using these to try to answer real questions around data. And that's how I ended up where I am today, I think.
Amazing. And now you're dressing up the veggies for everyone else to
Yes, yes.
dress. Awesome, Tammy.
Sure. Yeah, it's a great story, Monet. My beginnings were in the 90s. So this was pre-Google, just to be clear, the internet was new. And so I did my degree and my PhD in applied math. My bachelor's was in math. And I focused on linear algebra and numerical optimization. These are two good cornerstones to have for data science. But somehow Zoom is popping up a weird message. Sorry about that. So these are two good cornerstones to have for data science. While I was a student, there was a project that my boyfriend at the time, now husband, was doing for his job, where he was doing some data science type work, basically text analysis. So I got interested in this thing that was very popular at the time called latent semantic indexing. So this is working with term document matrices and essentially computing the SVD of these and then doing fun stuff. So I worked on that for part of my PhD, and the other half was sort of old-fashioned numerical optimization stuff. But there was no word data science at this time. And so, in fact, I wasn't sure what type of job to get, and I ended up going to the national labs and working on optimization. Mostly, I thought that's just what I would do. I thought I wasn't going to do data science again. But then the lab started doing early versions of data science, basically. After 9/11, there was a lot more interest in finding needles in haystacks. And so I became more and more interested in that and got into tensor decompositions, but also a lot of network analysis and other areas.
So thanks, Tammy. And Ray?
Yeah, so you actually prompted me to remember the answer to the question, because I wasn't even thinking about my undergrad, but you made me remember I was taking a mathematical statistics class from Jeff Whitmer at Oberlin. And I remember thinking in that class, I wouldn't know a Poisson distribution if it hit me upside the head on the street. Like, you know what I mean? There were no data sets in the entire class. And so I remember that we all said to Jeff at the end of this class, like, could you please do something actually with data with us? And I guess it was like a 2-part class or something, like maybe it was prob and then stats or something like that. And so he created a 1-class data analysis class that would be a companion to his statistics class, and it wasn't something he'd ever done before. And so I think it's really cool, first of all, that he was like, oh yeah, okay, I can do that. And then he took a group of us, and now, I mean, he's really run with that quite significantly since then. So I feel like maybe we inspired him a little bit. And I think that maybe came from an elementary school where, you know, we did math in our environment. So we had a whole week on something my teacher called the island, where we had to plan ahead all of our meals. We had to keep them all in a cooler, so they either had to be perishable or fit in the cooler. So we had an optimization problem. We had an optimization problem in that we had a budget, and we scoured newspapers to decide what we were going to purchase and what it was going to cost. We did all the shopping. And the amazing thing she said was that, you know, we had all the food from Monday through Friday there on the island, and nobody stole the chocolate that was for Thursday ahead of time. So there was also sort of fair apportionment and ethics involved in this whole situation. That was like 5th grade. So I think that I really grew up thinking that the math that you do has value and can help you solve a problem in a way that might be a kind of an optimization problem, even though you didn't know it, and you needed data, which was like, how much do things actually cost? And then this whole piece about, like, what do people actually want to eat? Like, what are people willing to eat? And the whole negotiation of coming to consensus on what to eat. I mean, all of that were super valuable skills to learn as a 5th grader or at any age. And then Out of college, I went to Carolina Friends School and taught for about a decade. And all the time I was teaching from 5th grade through 12th grade, I was always using data. Problems, I was lucky to be affiliated from high school with the North Carolina School of Science and Math, so heavily influenced by the data work that they were doing there. And teaching at the TIP program with their materials in the summer. So very influenced by the modeling that was being centered at NCSSM for a long time. And then, so I taught at Friends School for a decade, and I still wanted to learn more math. And I had done operations research with Bruce Pollock Johnson at Oberlin and had a practicum at NASA that was very influential in my thinking about, okay, you can do math lots of different ways. And I just really tickling my fancy to learn more math. And so eventually after a decade, I went to grad school, pretty sure I would not be able to do it because it had been like 10 years since I'd seen an eigenvalue. But, you know, knowing your high school math does not serve you so poorly. You know, when you're beginning college math, you've got that really down solid, you can learn just about anything. So, so I went to NC State, and I remember, you know, walking into Michael Scherer's office, my advisor, and saying, "What is it with these eigenvalues and eigenvectors? They are the key to the universe, but I still don't, I'm sure I don't have the whole picture. Can you explain it to me?" And he just looked at me and he's like, "I don't know what you're talking about." I mean, he did know what I was talking about, but he didn't exactly know how to answer the question. You know, like, I don't know. You use them, they're useful. What are you asking me? But I had this feeling, right, that linear algebra was the key to everything I was learning. And so even when I was learning differential equations, what were we doing? If we had something nonlinear, we were going to linearize it, right? If we had something to optimize, there was going to be some sort of, you know, some sort of aspect of, you know, some sort of series that we had truncated and we're using in some special way. Like everything seemed to be focused on that. And that was just so exciting as a thread. And then later at Harvey Mudd College, where I was another decade, you know, all of our clinic projects, which were industrial project capstones for seniors, they were all, for me, very fluids based, because I had done fluids, and they were very differential equations based for about 4 years. And then all of a sudden, every problem the industry was bringing us was anomaly detection, like Tammy was saying, looking for needles in haystacks or abnormalities. And every problem started being like, I have a data stream and I want to know when something's special or unusual, because I think the money, you know, like the advantage for my company is in being able to not just notice what normal looks like, but to notice what special looks like. And special might mean I need to wake somebody up because something's broken, or special might look like something's extraordinary, like the person who survives when everyone else is dying. And so, you know, I think, again, outliers can be both positive and negative. Always good to remember. And just like, it's interesting how it has always having data pop up has been a thread. And then the question about, you know, like getting into data science and AI, when I moved, you know, to MAA, the Mathematical Association of America, and had a wonderful AAAS fellowship and learned policy, which I'll probably talk about more, the importance of that, and decided to come back into an academic environment, it was really clear to me that I wanted to be in that data science and AI space, because I really felt like all of that grounding that I had from the rest of my career could help us understand the shifts and adaptations that all of us are going to need to make to try to use these tools responsibly and efficiently.
Awesome. Thanks, Ray. So you commented a little bit on some of these concepts that data science students are going to need to know, and how you think about that. So my next question for all of you is, what do you see as the core mathematical concepts that every data science student should learn, regardless of their background? And you can differentiate between backgrounds if you would like. Sorry, and I'll let now whoever would like to jump in first and feels ready to answer, just take it away. Yeah, Tammy, go ahead.
All right, let me see if I can share my little slide deck here. Okay, good. That looks like it's working. So I forgot to say this in the beginning, but it wasn't really my background. But I want to say a little bit that math is really a big key to AI. And I think we'll come back around to how to convince data science students to take math. So I think that's one key thing we should talk about. And I did this like a few months ago for another situation. I just looked at job ads with data science with the key math in it. And it's quite frequent. I mean, there's a lot of data science jobs that are not about building models and don't necessarily require mathematics. But there's the best jobs, the jobs with the best titles and having the most influence, have a big mathematics component, or at least having a strong mathematics background is a huge differentiator. You really can't get by without it if you want to be doing that top level data science. And then I also want to say that I want math itself. There's a lot of mathematicians here. I think math should change to make people better prepared for data science. Data science is not a thing that's going away. It's kind of everywhere. So not only do we need to be able to do data science, but we need to sort of flip and use data science. And then I'll skip ahead here. And then the key skills for data science. So, you know, we'll come back to textbooks and stuff, but one of the problems with teaching data science is the variety of backgrounds that people have. And I will be so happy when you can assume that at a sort of third or fourth year undergraduate level, they've already had some of these basics. But linear algebra, and there's a lot of different versions of linear algebra there. I was just talking to some folks last night, and they said, you know, they don't know the singular value decomposition, even though they had linear algebra. So some specific things, really including, you know, eigenvalue decompositions and SVD, which is not in a lot of first level books. Numerical optimization. I've seen people say, oh, they should know stochastic gradient descent. There's a lot. I don't think you need that. There's a lot before that. The basic concepts of gradients, especially matrix gradients. Those are actually pretty tricky. That's really more of a third or fourth year topic, maybe in graduate school. And then also probability. So the basics of probability. And it's pretty rare that you have these three. Even mathematicians don't typically have probability. So I really think that should be added to the curriculum. But then you're also, if you invent a data science curriculum, these are probably 3 separate classes if it's a really hardcore curriculum, or at least smooshed into one class, like things you might be asked on interviews that you should know the answer to. I'll stop there.
I'll try to jump in. I think another important concept is uncertainty and being able to make decisions in the face of uncertainty. I feel like it is quite possible to fit a model, like as in run the code necessary or push the buttons necessary to run a model someone else may have implemented, or a statistical procedure. But to be able to make empirical decisions in the face of uncertainty really requires having learned these like concepts and being able to think with them. And so I mean, there's a lot to a data science curriculum, and some of it doesn't necessarily touch on uncertainty. And I feel like that's like another thing to bring in. And I also like agree with Tammy. When I talk to our students and they're looking at some of the job ads, like the ones they're eligible for right after graduating from an undergraduate degree, and modeling isn't always listed there, but something I try to remind them is that if you genuinely want to have an intellectually rewarding and one where you can keep going up the rank sort of career in data science, these will be important for you. Now, maybe you go back and get a graduate degree, or maybe you try to learn some of that now to prepare yourself, not just for your first job, but the ones that might come after that as well.
Yeah, I'll just add on to that. Tammy, as I was looking at your slide, I did a lot of work with a kindergarten teacher on what kinds of modeling she could do. What kind of modeling can you do with kindergartners, and how can you give them problems that are open, not only at the beginning or the middle, but also, you know, not only the beginning and the end, but also open in the middle, open at the beginning. And these kindergartners, like the more open a question you gave them, and elementary school students in general, the more they showed math that the teachers didn't even know they had, because they were able to, from the beginning, pose a problem and then choose the math they were going to use. And when they chose the math, all of a sudden the teacher would say, I didn't know they knew that. Well, I didn't know they thought about it that way. And so students that they viewed that maybe could talk things but not write them down, for example, were able to demonstrate a lot of mathematics that if you were to formalize it, they wouldn't have been able necessarily to follow the formal patterns that maybe are developmentally should be happening much later than sometimes. We're trying to teach them how to write, but maybe we want to teach them how to reason, and then maybe later it's more important. Like some of them might want to write it down or draw a picture, but others might just want to talk it out for a while. So it made me think of that. I wrote down like what could you do in kindergarten to make people think about vectors, and just sort of like having them point places, right? Like everybody point a different direction. Like, what's your vector? Like learning about more dimensions, thinking about things in 3 space, not just thinking about things in 2 space or 1 space, because children understand that we live in 3 dimensions, right? And so, how I feel like in our math, a lot of times we're just stuck in 1 or 2 dimensions for so long when we're living in 3 dimensions. That really doesn't make sense. And so how could we do that earlier? And even gradient, right? We could talk about gradient. So how do we earlier not try to have them deal with derivatives or gradients formally, but how do we use the language of mathematics that they'll see later? So by the time they're learning about gradients and you formalize those things, they're like, well, I know what that word means. I know how it feels. And so I'm not trying to learn a word and the mathematics at the same time. But again, those language, associating a language with a concept, and kids ask the best questions. So a lot of times teachers say you can't do something like divide by 0. And we need to give teachers that language to say, here's what dividing by 0 would mean. And let's explore that. Let's, not call it a limit maybe, but let's play with that idea and what happens as you divide by something closer and closer to 0. So many concepts of mathematics, if we could introduce them in an informal way earlier, I feel like they would be more comfortable later. And the concepts of data science are so primed for that, including what's the data of the world around you. The other things I would emphasize are communication policy. And I think, you kind of said this was some sort of uncertainty quantification. And to me, the simple way of phrasing those questions is being able to explain what do you know? Maybe in a modeling terms, what's your goal? What are your assumptions? What are your constraints? What do you know? How do you know it? Right? And that could be a proof eventually, or it could be a source, and why that source is a good source. It could be because and then how sure are you? How sure are you of what you know and how you know it, right? And what are your error bars? And beginning to start to recognize it's okay to have uncertainty. There is uncertainty in almost anything. If you tell me you have an apple, well, I haven't told you what color it is. I haven't told you how much it weighs. I haven't told you if it has a lot of bruises, I'm not going to eat it. Or I love it that way, right? So again, in math, it's like math has perfect constructs. Like you can say 2, and you can have this perfect construct, but it's also messy because once I got 2 apples, are they the same? Are they different? I don't know.
My gosh, thank you all. So I think you've kind of mentioned some of the challenges involved in kind of communicating to students about data science. But I'm wondering if you could just sort of comment more formally. A lot of you have experience designing curricula, curricular programs, texts, thinking about how to communicate with data science students. I was just wondering if you could talk about some of the challenges you encounter in that role and how you have figured out how to address them and maybe haven't.
I'll give it a try first. So one of the things that my mantra when sort of designing curricula is let them eat cake first. Not just let them eat cake, but first. I think about having to wait for your dessert, but maybe not. And the idea being that, even if I'm thinking about, a semester-long curriculum or just a single lecture, single class, single module, I think it's super helpful to first show students the end point they will get to. This is a little perhaps easier to give an example of, and a data visualization is also something I teach a lot, but I'll show where we're going to end first. before the building blocks, and then we learn about the building blocks. You know, you get those fancy Lego sets, you know where you're going to get to, and it's still quite enjoyable to get there. Now, there's the creativity of being left with just building blocks and building stuff too. And I think there are some of us who really, with no instruction, can get to amazing places too. But I think just having seen some examples of these potential endpoints opens the creativity up for a lot more students. And I think that's important to think about. So, for example, if we're teaching modeling, you know, there's so many building blocks that can go into that. We could be starting with the linear algebra. We could be starting with the computation. We could be starting with the uncertainty quantification, or we can, I don't know, bring the result of an interesting model that have been used to make a decision that may have affected students' lives in some way, or build policy, something they may be familiar with, or I don't know, prediction for the result of a baseball game or something like that. And then say, well, how did they get here? Let's take a step back. And maybe it takes a whole semester to get there. Maybe it takes a lesson, but the idea being that they know where they're going. So I think my own experience of not getting where the linear algebra is going has been instructive for me to not try to leave others in that situation. And I do also think it's important to then build avenues for students to be able to diverge from that end goal and do their own thing as well. So all these things like open-ended projects and whatnot allow for that as well.
I can comment a bit. So as Jamie mentioned, I've written a book that's coming out soon on tensor decompositions for data science. And there was a few things we wanted to accomplish with this. And this is kind of based on my and my co-author Gray Ballard's experiences trying to present this stuff. I've taught short courses and so forth. So, you know, one is, you know, I already mentioned you have to have some background material. There's a lot of linear algebra that's required. We've debated how to teach it. We don't kind of have it as an appendix for the book, but a lot of people might spend some time on those basics up front, or at least refreshing them. But there's two things that we really wanted the students to have beyond just the math. So I've just presented the math, and then I think the students are really understanding it and walk away. And then I said, well, let me ask them to do some work with a data set, see how that goes. And then I would learn a lot about how much they understand based on their playing with the data set. And then, you know, then I said, okay, let me have them code it. And if you want to feel like a bad teacher, have them code what you just taught them. Of course, all of you who teach know, okay, this is just, it takes a while to learn things, no matter how elegantly you explain it. You kind of have to be exposed at it, play with it. And to code something is actually often considered that then you really understand it. So this is kind of showing deep knowledge if you can code something. But I really think that teaching data science should strongly incorporate encounters with data. And so as a professor or teacher of a course, you probably have to work on curating some data. This is not just handing them a data that's already come out of the blue sky and data has just rained down upon you. That's perfect. It helps if it's sort of at least real, and maybe depending on the course, it's even appropriate to have them take that data from its raw form to something that can be processed with what you're going to teach them. But somehow you have to be involved with getting data sets that will be illuminating. And then I also think it's really, you don't necessarily need this in every course, but to have at least some coding aspect. It might be taking pre-existing codes and applying them to the data, which is appropriate maybe when you're just learning the concepts. And then it also might be coding up the methods yourself to better understand them. And invariably, I have at least learned in my teaching that I've learned so much that I forget to say that they learned when they try to work with the data themselves, or that when they try to code something. There's a lot that comes out in those that I had long since learned and forgotten that I learned and forgotten to share. So it's kind of very instructive in both directions.
I love that. I talked about my first decade of life and my second decade of life. So here I'm in my third decade of work life at NC State. And I was brought to NC State to think about how in a large public research focused university, we could get data science and AI happening across the whole university. So in just 3 years, we declared that we're a data science and AI university. All of the deans are on board. Every department is thinking about its data science and AI learning pathways for students. And I think a big part of that was goodwill and collaborative spirit amongst the university. So I have to first credit the university and also just decades of strength in data science and AI across many, many different departments, so much that the institution just thought we can't put this in one college, department, institute, center. This needs to really belong to everyone because we have such depth across design, College of Humanities and Social Sciences, College of Sciences, College of Textiles, business. I've forgotten half of them and they'll kill me later. So yeah, there's 12 of them. And so when I came in, Allison Wilson and Emily Griffith, statisticians, had thought about 6 one-credit courses that they thought were really fundamental to data science, things like data wrangling, communication, ethics, R and Python in little bite-sized chunks, things like that. So 6 things. And if you want to see any of this, you can just go to a Go link. It's called go.ncsu, North Carolina State University, ncsu.edu/DSA for Data Science and AI Academy, just DSA anyway. And so on that website, you'll see we have a course model. So the very first thing I thought was, if we're going to do this across the whole university, and how am I going to get people to teach it? Because I don't have any faculty lines. So what if we got alumni? So I went on LinkedIn and started looking for alumni in industry taught at a university before or a college, and found some amazing people who had been in academia but went to industry and were sort of itching to teach a little bit, and got them to come teach a one-credit class and expand our offerings to whatever they needed at the time. So that's been a really successful one tactic, plus, encouraging faculty to come teach these as well, and postdocs, and occasionally graduate students. So when I thought, well, okay, these courses are going to we're going to stand up a bunch of them. We have 20 per semester now, so 40 a year. And what's going to tie us together if we're across all disciplines, across a huge university with 86 majors and, 12 departments and 150 programs of study? And so that we created a model so that every instructor would be, again, that modeling sort of perspective. They would have common goals, they would have common constraints, common assumptions, and then whatever they were teaching, they could exchange ideas. So actually on May 9th, we have our Adapt Share Fair, if you're interested, and our students are actually going to present on that. So you can follow up with me afterwards if you want that. Everyone's welcome. It's online and free. But these common elements, so there were 3 big elements, and it's been a work in progress. So we've changed these over time, but the first one has always been project-based teaching and learning. The second one are 10 things you should do if you're doing data science, like consider ethical issues, know what kinds of careers, are available. What are the open problems, and what are the recent interesting solved problems? Kind of like Mine was saying, start with something that was sort of recently solved and interesting that could inspire you to try to learn, like, how did they do that? Let's figure it out. Or maybe we can do it better. So anyway, there's 10 of them. And then the third element has had many names because that one's about having genuine choices. So Dan Teague from the School of Science and Math always talked about students need to have genuine choices so that when they get in the workplace and they have a choice to make, they have some experience making a choice that's actually going to make a difference, where they could have legitimately gone way A or way B and way C, and maybe one was better, or maybe 2 were equally good, but you prefer this one. And so how do you make those choices, at work, about how to work with a team and make choices? So that model has been incredibly important in order to form a community of instructors in data science and AI across many disciplines, many departments, many incentives for career success. And I think that the sign of the success is that those instructors are contractually obligated to meet every other week for an hour and discuss their teaching and learning in this model, but they meet more than that. And so I feel like the fact that, our industry folks are choosing, because it's a good community and they want to be continuously upskilling. So our instructors also have groups where they're meeting, because we know this stuff's changing. It can be so tiring and frustrating to be like, I thought I was on the cutting edge, or almost 5 minutes ago, and now I'm not. So again, like having a community of people is really important, maybe even more than the specific curriculum, because then whatever curriculum you have or whatever you're doing, you have buddies to help you. Again, you make a genuine choices and as an instructor that can adapt over time. So I would say in terms of curriculum, having an adaptable curriculum, and we call our curriculum ADAPT. Jamie said it, all campus data science and AI project-based teaching and learning. Like we call it ADAPT because we know that's what we're going to have to do. But we also know, we've got students all over campus that can benefit from this. It's also really important that you have baby steps and flexible pathways so people can jump in at the complexity level or challenge that's appropriate for them. But we have so many people coming out of high schools that have never had any coding, and we have people who've had 3 internships. And the coding piece of things, which is a whole other language, takes time, like Tammy said. You're just not gonna, no matter how well someone teaches it to you, learning a language, you have to practice it, you have to make mistakes, you have to get corrections. And so how do we take a whole population, including, by the way, some of our instructors and faculty who need to upskill, practically the whole government needs to upskill in these areas. And so how do we do that? And again, we use this same model, whether we're teaching for credit, not for credit, workshop, semester-long class, people in industry, people in government. We use the same model. We have some of the same instructors because we believe that that good learning environments have these qualities that are cross-cutting. I think you said, Jamie, like separate them into learner types if you need, but to me, it's like, get you what you need, but actually so much of the learning science says that the elements of good learning are really common because we're human. But the other thing I think that is hardest for me to think about how to make happen in data science and AI, not just in the classroom, but in the workplace is, okay, well, what if I'm blind? And we have so much emphasis on data visualization, and not as much broad data communication. Like, how do I make sure that my data communication can reach all audiences? What if I'm colorblind? What if I'm low vision? What if I am hard of hearing or deaf? What are the things that can really, that if we design them in, I would also be able to use these things to my advantage. And how do we think about that ahead of time? And how do we help our students be thinking about that and really look at the tools our students are using for that? So I know I'm talking long, but last example, I went to this wonderful talk by John Samuel, who owns a company, Abler, that helps people get access that are low in vision or blind like him. And at the end, I was like, okay, well, I had my PowerPoint and I did the accessibility tools and, like, does that help? And he's like, I'm never going to look at a PowerPoint. I'm never going to look at anything anyway, but, I'm never going to use a PowerPoint. I don't want my friend to read it to me. Like, send me a Word document and use the headers that say that the title is a title, that say that header 1 is a header 1, so that I can skim through the headers, I can get to what I need, and it works with my screen reader. And I was like, wow, that 4 hours of my life I'll never get back, but this 4 minutes has been very instructive. And so also, just you can think you're doing the right thing, but if you don't know your audience, you're going to totally miss. And you could spend all of the goodwill time in the world working towards making things better for people and totally fail. So, so again, just that piece is so critical to build into our tools and also to build into our work environments and our learning environments.
Awesome. Yeah. Thank you all, you three, so much. So I think I'm going to turn it over now to Dirk for a couple of questions, and just so that we can try to get through a few of the Q&A questions and then also through some of the submitted questions. We'll try to do a little bit more like rapid fire.
Okay. So there's one longer question, the Q&A from somebody who's teaching courses in data science, undergraduate and graduate. And it's a 2-part question, and they already give some part of answer as well. So the first question is, what is the math we should teach in undergraduate, master and PhD level? And second, what are the prerequisites we should push for in high school and undergraduate? And part of the answer is their pick would be more probability as soon as possible, linear algebra, and just the calculus needed for limits, infinity approximations, and also more function analysis for PhD. So it was their pick, but I'm curious to hear what you have to say about that.
Um, I'll try to answer part two. I mean, I have ideas for what we should teach at undergrad, like level, though they're not very different than I think what a lot of people are already doing. But if I'm understanding the second question correctly, in terms of like what should students be coming with in high school? Now, if there's a genuine mechanism to work with K-12 educators and policymakers to change things, like I think that's great. And I think that we need to be in those spaces as well. But I do 100% believe that once students get to our higher education institution, we can't have prerequisite expectations for them to participate in data science. So if it is feeling impossible to build a curriculum that doesn't rely on something from undergrad beyond just, I don't know, just like high school level generic math, I think, then I feel like it's time to rethink a little bit within the constraints of your school to try to make it just so anyone who is at your institution, if they're interested, could get through it. Now, I do understand that pacing may need to be different for students with different backgrounds. They may not all get to the same place at the same time. Those are obviously okay. We don't want to build structures that hold anyone back either. But I do think it's possible to start with your traditional Calc 1 or something and still build your way up to it, and also do so in a way where you maybe move some courses around where students are doing a little bit of these building blocks while also doing something where they're hands-on with data at the same time, for example. So that's my sort of half answer to the question.
I'll just shout out that Mine and Jamie and I are on a task force that's a collaboration between SIAM and many other professional organizations to try to come up with a list of what an undergraduate data science curriculum might look like. And our job is to make sure the math and stats is in there. And it is out for comment. So maybe Jamie and Richard, we can find a way to share that with this audience afterwards. So that they can take a look at those where we are so far in those materials, and then go ahead and add your own 2 cents about what we're missing. We actually want to know what we could get rid of because we have too much potentially, but we're working on it, and that'll be available publicly.
I'll just add, I really like the idea of doing more in high school. I think, at least when I was a student, they started calculus in high school. And it's such a wasted opportunity because probability is so much more interesting and inviting. There's so much you can do with just discrete probability at, golly, pretty early in the high school level. And it can be really engaging and I think much more interesting to a wider variety of students. And ditto for linear algebra, there's I think a lot of interest among high school students to start learning that because they are motivated by understanding things like deep learning and linear algebra I think comes even before the calculus. And so there's no doubt that calculus is really important, but I think that these can come before or in parallel with calculus and could be much more engaging at the high school level. And then for calculus, I think I agree with the asker that the calculus 3 semesters of calculus is sort of very old-fashioned and taught in a very funny way that's very unnatural and maybe overtuned towards engineering degrees of 50 years ago. And so it takes new books, okay? So it's not like it's trivial to just change that. We need new approaches to teaching. And if you've already had linear algebra, it actually opens a lot of doors to teaching calculus more efficiently, especially when you get to multiple variables, which is now done in such an awkward way. You almost don't even know that you're learning vectors. And yeah, I would really stress rethinking the curricula and what is taught in if we could affect what's taught in high school, I think it would energize math. And there is the great thing about data science to me, one of the greatest things is that it's made a lot more people interested in math. this has been the key thing, and this, math programs aren't necessarily eating it up because sometimes they're outsourcing these classes, but there's certainly stats programs have had to expand to incorporate all the masters that people want to get and to teach more classes. And I think math could be really involved in expanding their programs to serve a greater, the greater interest of students.
Yeah.
Awesome. Thanks. Dirk, were there other questions you wanted to bring from the?
There's 3 more questions, so these are kind of like more smaller and more narrow, but I think you can ask them anyway, but I probably will just need one answer for them. For example, one of them is how does linear algebra underpin key machine learning algorithms such as PCA and SVMs?
Can you say it again, Dirk? I didn't quite get
How
it.
does linear algebra underpin machine learning algorithms such as PCA or SVMs? It's, I don't know, I would also have an answer to that. It's basically just without, so of course you can use these things without knowing linear algebra, but understanding what they're doing is pretty much, yeah, it's probably not impossible, but I think with knowing linear algebra, you just have a solid understanding of what you're looking at. That would be my take on that. But if you have anything to add, please go ahead. Otherwise, I have 2 more questions here. So the other one is of a similar type. So what role
I
does
wanted to say
probability?
one thing.
Yeah,
I
sure.
think in a lot of classes, you learn a lot of linear algebra and then you see SVD. And you see it sort of as a technique to do linear algebra. But like Miné said, if you could start with SVD does something really important and interesting, like points to what you care about, then you say, how does it do that? And then the answer is linear algebra. I think that is another answer to that question that Miné already gave, but I would really point back to that, because then to me it comes again way too late. Like showing that cool application and then building a whole class towards, by the end of this class, let me show you this really cool thing you can do that you have no idea how we can do it. Everything we learn in this class, we're gonna point back to where it shows up in this algorithm. And so, by the end, they feel like they own something like that. Again, that will then come up in many a math talk or as long as they're staying in the world of linear algebra, they will hear those words again and can go to conferences and feel like when someone says that, they understand that inside and out. And when I say understand, I really mean could catch if someone did it wrong. For example, if it was improperly coded, could say, wait, that's not supposed to happen that way, like Tammy was saying.
Thanks. That makes sense a lot. So the other questions of a similar type and probably would get the same answer. So what role does probability theory play in modeling uncertainty, making predictions, and Bayesian inference and decision trees? My understanding is it's basically the same, right? You can use these stuff, but you can understand it better. And of course, when teaching, I totally agree with what Ray just said, right? Showing first, this is the stuff probability theory can do, and then teach that.
Yeah.
Anything to add? Go ahead. Yeah. Mhm.
And I think sort of having a good grasp of some of what we might consider the basics of probability also allows you to, take a look at a computer output and maybe be able to say, actually, this doesn't look right. Like, based on what I've seen about this data set, I don't necessarily believe these estimates being reported. And it may genuinely have been an error made along the way. But if you're, one, not looking at your data ahead of time, and number two, don't have sort of a good grasp of some of the mathematical underpinnings that these procedures are built on, it's a lot harder to be able to have that insight. Another way you can have that insight is knowing something about the domain where that data is coming from. But I'll at least speak for statisticians. Oftentimes we're plugged into projects where that is not our expertise. Like I may not know something about this medical application. A doctor who might be working in that area might look at the numbers and be like, I don't believe that. And that's also super useful. But for the person coming at it from the data science, statistics, mathematics perspective, without the domain expertise as the person who gets plugged into these things, what we have in our toolkit are both our ability to sort of parse through data and have some expectations about what the results might look like, but then also be critical of those in case there are, things we want to fix along the way or things that don't make sense.
If I can sort of riff off of Mina's answer, one thing I think that you learn through these things is, both the foundational parts that you need, but there's also a mathematical thinking that can be really valuable in data science. I've heard, so I do consulting and I hear occasionally complaints about data scientists not having common sense, okay? And this means they don't really understand their data. They don't understand that they're not asking questions. They're just putting data into methods and getting out answers. And they're never being curious about if those answers make sense. If not, why not? And this can involve understanding the mathematics, but there's also a key component of mathematical thinking that's extremely valuable. And so whatever math classes people take, I hope part of what they get is not just the mechanics of pushing things through, which often, you have to do that at some level in the very earliest classes. But this is why I'm excited about like probability theory. It can be one mechanism to learn how to think, even as early as high school. So there's a lot of options here that I think go beyond just knowing the foundations mathematically.
Yeah, and I think a lot of people who think they understand what math is, if it's more like balancing a checkbook, think of it as very deterministic. And a lot of the math they did in school, like Tammy's saying, was very deterministic. And so then when they encounter a large language model, for example, that a lot of humans are playing with, they don't think of themselves as doing any math. And they get surprised by what comes back. I would love for them to understand two things. One is, why would incorporating probability into the model make the model possible in the first place? Why can it do the thing it does? Because it incorporates ideas from probability. And then secondly, because it needed that in order to be so powerful and incorporate aspects of probability and statistics, because it leveraged those things, in order to even be able to do what it is also introducing randomness and uncertainty and errors that you have to be aware of. And so that would also help them be more appreciative of the math that's helping them do what they do, but then on the output, understand why they have to check their work. And so while I don't know that this will be the case, what I said at Harvey, but in the clinic problems, as we were transitioning to doing machine learning all the time, because it was so new and the students were so excited, they wanted to be developing till minute like 59 out of 60. And it was so hard. Like I was trying to ask them in like after a third of the year to say, how do you know what you're doing is what you think it's going to do? How do you know what the bounds are on what it actually can do and when it's going to fail? Because what you don't want to do is hand something to someone and say, this is going to work, instead of saying, this is going to work under these circumstances. And my naive hope is that, having more AI/ML/probability built into things so that people are more, they're more aware of that uncertainty. Because when I try to type a word, I get a word I've never used in an email before. And I'm like, okay, clearly that wasn't my distribution. That was somebody else's distribution, right? That viscerally allows people to realize that putting something in isn't going to automatically get what you want. It's going to depend on how somebody programmed it in the first place, what data went in order to determine what you're going to get out. And again, maybe that's naive, but I feel like if more of us can communicate those things to the general public, at least they could be skeptical of the output and asking questions about the input, and even perhaps asking questions about what's happening in the middle.
Awesome. Yeah, thank you. Okay, so I'm going to really quickly address one of the questions in the chat which first included a big thank you to you all for this being such a useful event. And then secondly, I'll be asking our panelists to share with me afterwards slides if they're comfortable with that, any of the resources that they've mentioned, links, etc. And we'll I think we'll be able to get that out to all of the participants. If not, I'll post that on Engage later on. Okay, I'm going to turn it back to Dirk for one more question.
Yeah, there's two kind of like the same questions here. It's basically about the role of mathematical proofs in undergraduate or data science courses. So I think it relates to this mathematical thinking somehow, but probably there's also more to that you can add.
I don't really teach mathematical proofs myself, just based on sort of my department and the courses I've been teaching. But I think one way, therefore, I'm like the worst person to be trying to answer this question. But one thing I do, like in a course we have recently revamped our probability theory course, is that we teach mathematical proofs, and then we have a lab section that goes with that, and then we go over the same thing and write a simulation to sort of do, I don't even, a computational proof, if you will. And I do think that that thinking back and forth, sort of trying to answer the same question, but with different tooling, I think is very useful. And it is something that we hear from our students to be something they appreciate as well. Some students excel at one and find the other one harder, or vice versa. But also, even if both of them come easily to you, or you're struggling with both, the idea that there is a question you're trying to answer and there may be different pathways you can get to that answer equally valid is a good thing to show. So I don't know if this is sort of the intent of the question, but I do want to say that I think they have a place, one, and I think they can be augmented, particularly in a data science context, in other ways as well.
I want to speak up to a little bit of back to the communication and maybe I love proofs. I also think that when mathematicians are trying to make any argument in life that isn't a mathematical proof, because they're a mathematician, we tend to sometimes think that if we are logical according to our logic, then someone should agree with us. And if they don't agree with us, it's because they didn't understand our logic. And since we are here with the Society for Industrial and Applied Math, I'll say that one thing that you get from doing modeling that you may not get from doing proofs is understanding that your argument depends on your goal, your assumptions, and your constraints, and then your logic that moves from those things to a conclusion that necessarily has potentially uncertainty, etc., right? And depends on those assumptions being valid and common. And so for me, in this world where we so easily are divided and around people we don't agree with, I think that modeling has a potential to help us understand each other. Because if you can just understand what someone's objective is, what their assumptions are, or what constraints they think they're working under, you can at least understand why they're going the direction that they're going. And so I think that proofs for mathematicians are our logic, our way of knowing when we truly are certain, which is rarely, but in math, more often maybe than in almost any field, we can be absolutely certain of things because we have a proof, and that's a pretty privileged, wonderful place to sit, is to really truly know things, as long as the proof is airtight. And I love that about math, and that's why I fell in love with math. And I fell in love with applied math because it's helped me understand people I disagree with and the messy world that we live in.
I'll just add that I think proofs are useful in understanding things more deeply and the question. So, now there's lots of questions like, what's the role of proofs if an LLM can prove things? I mean, they can't, okay, for the most part, they can't prove anything, especially anything original, but it's interesting to reflect on the role of proofs in our own insights. I think learning the ability of abstraction is something that comes with doing proofs. It's kind of like coding something. If you can prove it, you probably understand it. And there's many ways to go about proofs. that can lead to the same conclusion. So it allows for an element of creativity. And what I love in math is when we try to find the perfect proof that's from the book.
Mhm.
And there's crossover to learning how to write, because I do think writing also can have can be that crossover between that having that most elegant, logical way of creating an argument, and then also sometimes including those messy elements as well. So I think for me, I was a math and an English major, and I've taught a lot of first-year writing. And so for me, there's nice connections between mathematical writing and composition writing or rhetoric.
So awesome. Yeah. Thank you so much. Okay. So I think this is a great note actually to end on. I want to thank our panelists for their time and their really great conversation in this space. And we'll wrap up there. As I said before, I will be soliciting the panelists for anything that they'd like to share via email or on Engage, and we'll post that soon. So thank you all.